Hey everyone, this is Dr. Walker. This is video 84C on the physical pendulum. We just talked about a simple pendulum where you had a mass on a string and we completely ignored the mass of the string. All the mass of the object was concentrated where the mass was hanging on the string. So the physical pendulum is a little bit more realistic because it can be any kind of hanging object, and it's just going to be oscillating about any point other than its center of mass. The object cannot be approximated as a point mass because the size and the shape of it is definitely going to affect its rotation. So let's derive the equation of motion for a physical pendulum. What we're going to do is we're going to start from Newton's second law for rotational motion. The net external torque equals the moment of inertia times the angular acceleration. Now we're going to plug in what we know. So the torque on this object that's causing the rotation is due to the weight of the object which acts at the center of mass. So if you can draw a line here, this is the force line. And now, in order to find the torque produced by this weight, if the pivot point is over here, what we usually do is we extend this force line so that we can draw a line that is perpendicular to that force line, and that's our moment arm D. And that's what has been done over here. So the moment arm D, in this case, is D sine theta, because we're calling D to be the distance from the pivot point to the center of mass. So that's where the torque comes from. We have our force times our moment arm. And this is equal to I, and we can write the angular acceleration as a second derivative of the angular position. Now we're just going to solve for this term, which is the angular acceleration. So we're just dividing everything by I. And we're also making the same small angle approximation that we made for the simple pendulum. For small angles, and this is typically for angles that are smaller than 10 degrees, then we say that the sine of theta is approximately equal to theta. So that's where our sine of theta disappeared to theta here when we solved for the angular acceleration term. And now we're going to make another substitution for omega squared. We're going to call it this whole coefficient here, whatever's in front of theta, mgd over I. So our equation reduces to this form, which looks very similar to the one that we had for the simple harmonic motion for the spring and for the simple pendulum. So what's noteworthy from this, for this physical pendulum, is this definition that we made, right? This is going to give us the angular frequency, how quickly this is oscillating, right? How many cycles per second. So from this definition that omega squared is mgd over I, then we just take the square root, and now we have our definition for angular frequency. The same way we had omega equals square root of k over m for a mass on a spring, for instance. From this definition, we can also calculate the period. Remember that omega is equal to 2 pi times the frequency. And the frequency is 1 over period. So 2 pi over period. So that means that the period is equal to 2 pi over omega. So that's how we get our expression for the period. We do 2 pi divided by all of this omega. So just like with the spring and with the simple pendulum, we see that the period of oscillation is independent of the amplitude. If we can actually calculate the period of oscillation of an object that is oscillating about a point, and if we know where its center of mass is located, that means that we know this distance d, and we can calculate the period experimentally, right? Then we could actually figure out the moment of inertia of that object. Let's look at one question. It says, a solid disk and a circular hoop have the same radius and the same mass. They can swing back and forth as a pendulum from a pivot at one edge. So that means that they're acting as a physical pendulum, right? A physical pendulum is anything that's oscillating about a pivot that has some certain size or shape that cannot be approximated as a point mass. So which one is going to have the larger period of oscillation? Well, we just learned the equation for the period. Period is equal to 2 pi square root of I divided by mgd. So go ahead and think about this question for a second. Pause the video. So the one that has the larger period is going to be the one that has the larger moment of inertia, because they all have the same mass and they're all going to be pivoted about the same distance from their center of mass, because their center of mass is in the center. So they all have the same distance d. So everything is the same except I. Do you remember which one has a greater moment of inertia, a solid disk or a circular hoop? It's a circular hoop. Remember, the moment of inertia of a circular hoop is mr squared, while that of a solid disk is 1/2 mr squared. You can get that from your equation sheet. So we have our answer. The one with the greater moment of inertia is going to have the larger period. So the answer is B.